There we go. Okay, so I need to talk to you guys about inverse functions. I'll remind you to start with that, if y equals f of x passes horizontal line test, right, then f of a equal to f of b implies a equals to b, right? In other words, f is injective. So an injective function, in short, is a function that for a given output which is attained, like the only way that output can be reached is by that one input, right? There's not two different inputs that give the same output. And so what that means is that you could define, if you had a function, right? And let's suppose it went from A to B, where A is, well, we usually call A the domain of f, right? And I'm going to assume now that B is equal to the range of f. And suppose f is 1 to 1. So 1 to 1 is another synonym, the same meaning, different phrase, same idea of injective. Like 1-to-1 function is an injective function, okay? And in our context, that means it passes the horizontal line test. So if you have such a function, then f inverse is a mapping from B to A defined by f inverse of y equals to x if and only if y is equal to f of x. So this is how you define the inverse function. It does the opposite of the function. All right? Now, so why does that make sense? I mean, do you see why the 1-to-1 is needed? F inverse of y equals to x. So in order for this to make sense, in order for f inverse to be a function, we need that the inverse function assigns just one value, right? That's the definition of function. And so we get that because the f is 1-to-1, right? That means that the input x mapped to y under f. And that's the only one that mapped to y. So that's what's needed. Now, let me make some other comments here before I get into actual examples with formulas and such. Some other things we should notice. One is that there's this like really neat interplay, right? So the domain of the function in this context is equal to the range of the inverse function, and vice versa. The range of the function is actually equal to the domain of the inverse function. So this is the interplay between domain and range for the function and the inverse, right? It's kind of like traveling back and forth from work to home, right? Like if you think about that as a function, when you travel from home to work, home is your domain, work is the range, right? When you travel back, your workplace is your domain, and your home is your range. If you think about the reverse travel in terms of like, think about it as an inverse function, you could think about it that way. So again, a picture that I draw, a mental picture I draw to help me out is this. I think about this as being the domain. I think about this as being the range. And I think about x being here, and then f maps it over to y equals to f of x, right, over there. And then F inverse maps it back. So we can think about it like that. So the other thing I should mention is there's another way of writing this definition, which is also helpful. I think I wrote that for you last time. I'm going to write it again, which is we could make the definition for inverse as follows. We could say the F inverse is defined by, so we need two things. One, we need that F of F inverse of y is equal to y. And two, we need that F inverse of f of x is equal to x. This is for each y in the range of the function, and this is for each x in the domain. These are also things we know about the inverse function and we should be willing to use, right? Like that's especially important, what I just wrote down, these 1 and 2, these are especially important if we're like trying to solve equations and we want to get rid of an inverse function. Or if we want to get rid of a function, we can take the inverse function of both sides and basically cancel the function out with its inverse under composition. You do that, especially in the second semester, when you look at trigonometric functions, you might take the inverse trigonometric function to kind of get rid of it. Okay, but that's just a forward-looking comment. The other thing I should tell you, before we get into, again, numerical examples, is the relation between the graph of the function and the graph of the inverse, right? So, put it down here. Basically, here's the story. I'll make it a remark. So what was the graph of the function? Do you remember how we defined graph of a function? It was the set of ordered pairs, right? X comma what? X comma y such that what? What's the condition for this point to be in the graph? What do we need? Of course, x has to be in the domain, right? And what do we have to say about y? How is it related to f if it's on the graph of the function of f of x? Right, y equals f of x. That's the equation for the graph. So, of course, what would the graph of f inverse look like? The same thing, right? Except instead of having, would be the domain of f inverse, right? And y equals to f inverse of x, right? So for that, I'm going to need to like take the, if I already have a function, if I already have a formula for the inverse function in terms of the variable y, like I'd have to change the y to an x to make a connection with what I just wrote. But let's try to unwrap this. What is this? The graph of f inverse. What can you tell me? X is in the domain of f inverse. How would we understand that in terms of the original function? That would mean what? This would mean x is in the range of f, right? And what would this mean? This would mean that, well, let me do it this way. This would be, if I take the function of both sides, I get f of y equals to f of f inverse of x, right? Notice that x here is in the range of the function, right? So it actually fits under condition 1. It's just I've used the letter y instead of the letter, I've used the letter x instead of the letter y here. But anyway, the point is, if we take f composed with f inverse, we get back to the thing again. So we get x from that. So what I'm trying to tell you here is that the graph of y equals f inverse of x is given by f of y equals to x. What is that? I mean, you're like, well, that's really weird. What do you mean by that? What I mean by that is if you want to graph the inverse to a function, all you do is you switch the roles of x and y. And that gives you the graph of the inverse. So let me actually do that for a specific example. So like, let's see here. So if it's going to have an inverse, I need to come up with like a one-to-one function, right? So something like, let's see here. Let me go from, that looks like minus 3, comma, I don't know, 3. And I'll go over here to, let's say, 2 comma minus 2. Oh, yeah, 2 comma minus 2. And then I'll go up here to, let's say, something like, I don't know, what's that, 5? Oh, yeah. Thank you. My bad. And I'll make the function relatively simple. Like, in the sense, I'm just going to connect the dots, right? Now, my question to you is, this function I've just drawn, y equals f of x, right? Is this an invertible function? I'll do the easier part. What's the domain? And they're included because I didn't put any, what's the range? Negative 3 to 3. Okay, yeah. Very good. All right, so let me put the red comment above. What I'm saying is that if xy is in the graph of f, then yx, so my handwriting is degenerating into too small. Let me make the font bigger. If x comma y is in the graph of f, then y comma x is in the graph of the inverse function. And you can use that sentence I just wrote as a template for how to graph the inverse function from the given function. All right? So I'm going to make the inverse function red. And I'm going to start with this point, 2 minus 2, right? So what happens? We flip the x and the y. Negative 2, 2, right? So and how about this 5, 3? That flips to 3, 5, right? So it's like up here somewhere. And how about this minus 3, 3? What happens there? It stays the same, right? And then you can just connect the dots. There's a theorem that says that the inverse of a piecewise linear function is, again, a piecewise linear function. This is called a piecewise linear function because it's made up of pieces, each one of which is a linear function. Mathematicians are kind of unimaginative in their naming of things sometimes, right? We're not like physicists. Physicists come up with all kinds of weird names for things like quarks, and start calling abstract things colors, and all kinds of crazy terminology in physics. And the chemists talking about electrons being happy. Us math people, we just call things what they are. Anyway, so there you go. That's the graph of the inverse function in red. Y equals f inverse of x, right? And what people usually describe this as is they say that you can make the graph of the inverse function by taking the graph of the original function and reflecting it across the line y equals x. Where's the line y equals x in this story? It's right here, right? It's the line through the origin. It's this guy. This is y equals x. So you can see that the graph of f inverse is the graph of f reflected across y equals x. So one of the things that means in particular is if your function happens to cross the line y equals x, any point where it crosses will be fixed. Like that's also going to be a point in the inverse graph. In this case, minus 3, 3, that happened. Okay? So let me show you another example graphically. And then I'll get into the formula stuff, okay? Oh, hey, can you tell me one thing more before I leave this example? Did my prediction about domain and range play out? What was the domain of the inverse function? It went from what? Negative 3 to 3, right? That was the range of the function, right? And how about the range of the inverse function? It went from minus 3 all the way up to 5, right? So those are a couple of good kind of gut checks to see if you're doing this kind of problem, right? You can check on this. Example 2. Let me show you something. So the let's see here, if I go like these. So this point is what's called pi over 2. And this point over here is at minus pi over 2. And it's going between minus 1 and up here is at 1. This is what's called sine x, the sine function. Y equals sine of x minus pi over 2 less than or equal to x less than or equal to pi over 2. You know pi, right? It's the ratio of the circumference to the diameter of a circle. It's about 3.1415, blah, blah, blah. Who knew all the digits to pi? Oh, man. So we've lost it. We don't know the digits to pi anymore. I mean, I guess you could check could like put it in your phone, right? But anyway. Okay, so there's a function. Is it 1-to-1? I mean, yeah, the restriction of the sine function from minus pi over 2 to pi over 2 is 1-to-1. And so like basically the thing to do is to think about these particular points. Like that point right here is what? It is minus pi over 2 to minus 1. And this point up here is the point pi over 2, comma 1, right? Oh, you got me. I didn't see you move it. All right, so those points for the inverse function, where do they go to? It goes to, and pi over 2 is about 1.5, okay? 1.6. What's that? With this point here, minus pi over 2 to minus 1 on the graph of the function, what point does that reflect to for the inverse function? We have to turn it over, right? This -1, negative pi over 2, right? And that's, to a good approximation, like -1, minus 1.6, all right? So that, it's closer to the y-axis, right? And it's further down. So it's like down here somewhere, basically, up to the limits of my graphing here. So it flips down there. And this one up here flips to 1 pi over 2, so that's like up here somewhere. Right? This point in the middle is the origin, right? and that one is fixed. Like the origin 0, 0 goes to 0, 0. So the origin is shared both by the graph and the inverse. And so what I'm trying to get to here is just that the graph is, see if I can do it right. I'm trying to remember if it crosses or not. I don't think it does something like this. It's hard for me to tell because my axis isn't quite, you know, what's the word, to scale, but it's basically something like that. If I was graphing it, if I was doing a really good job, you'd be able to see that the inverse function to that sine function is the same shape as the sine. It's just going up the y-axis rather than going over the x-axis. But it's otherwise, it's like the same wave, just gone. So like, what I'm trying to say is it would be like this. If I had my scale like just right, it would be like that. Whereas the function, original function is, you know, same shape, but this way. I get into trouble when I try to draw them both on the same graph because I just freehanded it. Yeah. So there you go. That's the inverse function. Y equals sine inverse is what I've graphed in red there. And so it's kind of neat. The original function, if you can look at it real careful, right at the endpoints, it's kind of like leveling off. It has what's called a horizontal tangent there. If you were to draw a line that would just touches the graph at one point, it'd be level. If you look at the inverse function, that horizontal tangent has turned into like a vertical tangent. So this is another thing we see if we study functions versus inverse functions. What's a horizontal tangent for the original function will become a vertical for the inverse function and vice versa. So there's some patterns to look for there that it'll improve your graphing if you think about it. Okay, enough of that. Let us get into the formulas. So I think last time I wrote down a method for doing it, right? I gave you an algorithm for finding the formula for the inverse, didn't I? Like step 1, step 2, step 3, something like that, right? I think I did it for f of x equals to the square root of x. Is that right? Yeah? All right. Let's do another example. Example 3. So let's let f of x equals to x over 3 minus 2x. All right? Now, this is another thing to think about. So technically speaking, I need to know that this function is 1-to-1 before I find the inverse of it, right? But the fact of the matter is, if you go through the steps to find the inverse, and you can't do it, if you can't actually execute the steps to solve for the inverse function as I'm about to describe, that will actually reveal to you that the given function that you're looking at is not 1-to-1. Like if you look at the algebra that fails, it'll pretty much show you why that function doesn't have an inverse. So like, I'm not particularly concerned with knowing whether or not a given function is actually 1-to-1 when I go into this calculation, because I know if I go through the steps we're about to go through, it's going to reveal itself if it's not possible to find the inverse. So step number 1, we're given the formula, right? Step number 2 is we write y equals to the formula. All right? So I think I called that step number 1 last time. Step number 2, solve for x. How are we going to solve for x? We're going to solve for x equals stuff in y, I think is what I said, right? How are you going to solve that? How are you going to solve that for x? I think we're going to need to use algebra, right? That seems fair. Let's cross multiply by 3 minus 2x. We've got y times 3 minus 2x equals to x, right? And then I'm going to distribute. I got myself a 3y minus 2xy equals to x. I want to isolate x, right? I want to get all my x's on one side so I can solve for it. So I'll say, okay, so 3y is equal to 2xy plus x, right? So let's move it 2xy to the other side, makes it plus. At that point, I see, hey, wait a second, I can factor x out of the right-hand side, right? I can factor x out. This is equal to x times 2y plus 1. And at this point, we're almost done with step 2, right? All we got to do is divide by 2y plus 1, and what happens? Yeah, x equals to 3y divided by 2y plus 1. All right? Step 2 is complete. Now that allows us to move on to step 3. Step 3 is what? Basically, write the answer. So step 3. So f inverse of y is equal to 3y over 2y plus 1. There you go. That's the inverse function for f. Now, how can you check that the inverse function that you calculated is actually right? What would you do to check your answer? So the usual answer I get at this point is something along the lines of, I don't need to check answers, it's fine. We trust you. Something like that, yeah. But I think it's instructive for you guys to check an answer. So let's do it. So we should check f of f inverse of y, right? How's that going to work out? So that should be what? F of 3y over 2y plus 1. Now, one way you could think about f, and so like this is another way of imagining like function operation, and you take the formula, and instead of writing x, you could think about like f of a box, right? Whatever goes in the box goes there, right? And the formula is whatever's in the box divided by 3 minus 2 times whatever's in the box, right? That's a way of kind of conceptualizing the formula for a function. Think about it in terms of a box that you're putting things into, right? And you have to sort of bubble wrap it or send it on its way in a particular way, just like that. So this function, I'm supposed to think about putting this into the box, right? And so the answer is 3y divided by 2y plus 1 divided by 3 minus 2 times what is in the box? Well, 3y divided by 2y plus 1. So at this point, you might be a little concerned because it doesn't, I mean, what is this supposed to work out to? If this is indeed the inverse function, it's supposed to undo what you just did. So you guys are telling me what algebra to do? What would you do? How about this? If I had like 3/7 over 1 plus 2/7, how would you simplify that fraction? What'd you do? I'll tell you what I would do. I would multiply that by 7 over 7. See, because multiplying it by 7 over 7 clears out the fractions. It gives me 3 over 7 plus 2 when we distribute the 7 through upstairs and downstairs. So in the same way, when I look at this, I see compound fraction. So what I'm going to do is I'm going to multiply by the denominator that appears top and bottom. I'll put it in red. So I would take this. I would multiply by 2y plus 1 divided by 2y plus 1. The reason I would do that is because I can do that. It's multiplying by 1, right? And it's a good thing to do because upstairs, we cancel the fraction. We're just left with what? 3y, right? And downstairs, we're left with what? 3 times 2y plus 1 minus 2 times 3y, because the denominator cancels. What happens there, though? You get a plus 6y, you get a minus 6y, and this simplifies to 3y over 3, which of course is just y again. This is what should happen. If we calculated the inverse function correctly, when we compose the inverse function with the function, it should do nothing. They're kind of, it's an inverse in the sense of composition of functions, right? Now you've talked about 3 different kinds of inverse in this course, if you think about it. We talked about the additive inverse of a number. Like 5 has additive inverse minus 5, right? 5 plus minus 5 is 0. We talked about the multiplicative inverse of a number, like 5 times 1/5 is 1, right? Now we're talking about the inverse of a function with respect to composition. That means that it's a new operation on boxes, if you will, that undoes the operation which is given. So if the function was boxing things, the inverse function would be unboxing, right? You can think about it that way. Or you could think about it in terms of, like I said, putting socks and shoes on or something. I don't know. All kinds of things you can think about, but there it is. So, one more example, then I'll let you start your quiz, okay? I should say bonus quiz, right? Let's suppose that we had f of x equal to x squared plus 9. And I'm going to say find f inverse of x if possible. So let's just go through these steps again, right? And by the way, what would f inverse of x been for my previous example? I forgot to write that. If you wanted it, what would f inverse of x be? If you wanted the formula in terms of x, you could do that, right? You just do 3 times x divided by 2x plus 1. I mean, sometimes we like to write the formula for the inverse in terms of x. That's an easy thing to do. We just take what we had in terms of y and replace the y with x. It's no big deal. Okay. So over here, step number 1. Y equals to x squared plus 9, right? Step number 2, solve for x. What's that look like? Looks like we've got x squared equal to y minus 9, right? And here's where we get into trouble. What happens when we take a square and try to get rid of it? We do what? We take the square root of the equation. But when we take the square root of the equation, what do we have to allow for? We have to allow for plus minus, right? So this gives me x is equal to plus or minus the square root of y minus 9. And so that reveals, no, unless you give me more fine print, there's not an inverse function here. Is this surprising? So, uh-oh. Not a single value, right? In retrospect, what could we see? If we were to graph y equals x squared plus 9, which we could do with our newfound transformations of graphs ideas, right? It's the y equals x squared graph shifted up 9. So we don't need a calculator. We should know that that looks like what? Parabola opens up, right? Like these. I mean, that's y equals x squared plus 9. And what can you tell me about that? What does it fail? Exactly, it fails the horizontal line test, like so. And in fact, that's what the plus minus is here. You know, plus or minus, if that green line is going through y, at plus or minus the square root of 9 minus y, that's where the points of intersection are for that horizontal line. That algebra reveals that. So if you do the algebra correctly, the impossibility of finding the inverse will just kind of naturally arise as you do it. How could I make this function invertible? What would I have to do? It's pretty simple. What term and condition could I add to the problem to make it invertible? What's that? X. I mean, yeah, well, what do we need to do to x for the original function? So here's some modifications. Number one, if we say that the domain of f is equal to 0 to infinity, then we can find f inverse of y is the square root of y minus 9. So that would basically say take the graph and just use this part, right? Yeah. The other thing we could do is we could try just making the domain of f minus infinity to 0, right? In other words, we take the graph and just do that part. So with those changes, we're going to pass the horizontal line test because we don't cut through both points. What's the formula for the inverse in the second case? Instead of choosing the plus, we choose the minus because the domain is negative, right? So we do minus the square root of y minus 9. So that's that. So I guess the most challenging kind of question I could ask would be something along the lines of, here's a function, is it invertible? If not, change the domain to make it invertible, right? That'd be a challenge question on your next test. All right, well, with that, let me turn that off and let you guys get started on this.